Welcome everyone. We're doing an emergency news section because there is a important security vulnerability that you should know about. We're going to cover the vulnerability really quickly, what you can do right now, what you can do today, and then we're going to move on and dig a little bit deeper into what actually happened and how they found out about this and see what we can't learn ourselves. All right, let's jump into it. So, regression. Let me turn the music off. There we go. There we go. Music off. Regression, a remote, unauthenticated code execution vulnerability in OpenSSH server. Now, a surprising thing that I saw with this was it was only an 8.7. Remote code execution, 8.7. And I have a theory as to why it got what I consider a low score. But yeah, remote code execution, kind of something that's super scary because they can execute arbitrary code with elevated privileges on your machine. So let's jump into it. So basically, the reason it's called regression is this is actually something that was solved back in 2006 was the first time there was this error that caused this issue, and it was actually solved back then. And it came back by a bad code commit. Now, that being said, we're not pointing fingers at anybody because when you get into this, you're gonna see just how brilliant the people that are working on OpenSSH have to be. And I say that because my goodness, there's no way I would never have caught this as well. Now, the thing is, and the reason I titled this that patching will make you vulnerable is there's certain I will pull up. Actually, let's pull that up right now. The reason I say that is if you're on Rocky Linux 8 or you're on Rocky Linux 7, both of those actually don't have the vulnerability because they're before the actual issue happened. And Rocky Linux 9, if you were to update to Rocky Linux 9 right now, it didn't have it as of July 2nd. Now, they were working on it with Red Hat. I'm sure that they'll have a patch either by the time you see this video or by tomorrow morning, easy enough. So you probably should patch as soon as that's done. But the reason I said that is a lot of the times if you were actually on an older version, you don't have it because it isn't a regression. So that was an interesting, little interesting note there. Okay, so anyways, what do you need to do? What do you need to know? And then we'll get into exactly what happened. What you need to know is that this right here, versions earlier than this are vulnerable to this, and they're patched here. So basically, they've come out with a new one, and they were patched in 2006, like I said, in 2006. This is when it was originally fixed. And then it was resurfaced in this one here. That's kind of the end game there. Now, what I want us to jump to is basically immediate steps to mitigate risks. If you guys are running OpenSSH servers, let's talk about immediate steps to mitigate those risks. So these guys are obviously way more experienced than I, so I'm going to acquiesce to their things. But this is what I would consider defense in layers here, where you want to Shrek it out here. Be that onion. I don't know if you guys are old enough to have seen Shrek. Are you? I'm just gonna go with yes. Hopefully you've seen Shrek. If not, tonight's homework: go watch Shrek. Then you'll know defense, onion, have a lot of layers. Anyways. So basically the easiest way is just don't expose OpenSSH to the public internet. Then obviously patch management, update as soon as you have a patch that fixes the issue. Network segmentation and intrusion detection. Now, the intrusion detection is actually a really interesting one because you're going to see, and this is one of the reasons I think that it got a 8.4 instead of a 10 out of 10, is it should actually be fairly easy to detect if you're being attacked. It requires effort and time. Unless you're just insanely lucky, it requires doing a specific thing over the network. And so good intrusion detection should actually detect this. This is actually when I will go back, and I know I keep harping on this. I think that a really advanced statistical analysis would be fantastic at catching something like this, where you're detecting anomalies, because what they had to do to get this to work would be an anomaly. No one would actually use OpenSSH this way. All right. Let's jump into it. So this is the basics for understanding it. So if you were here just to understand what the immediate steps are, read these and do these. Talk to your security expert. I'm not a security expert. I keep learning every single day. I learn more on the security side. It's interesting, but yeah. What's up, Apollo? All right. So let's get into the write-up. This is actually pretty long. I haven't gotten through the whole thing, but I was pretty excited about it because I actually think I could learn more from these than I generally give them credit. A lot of times I skim over them, and I was digging into this one more. And yeah, I was learning stuff from it. So I actually learned new words based off of this write-up itself. So if that there is things in the Linux kernel I didn't know were words, and maybe I shouldn't have admitted that. But anyways, let's get into it. OpenSSH is one of the most secure software in the world. This vulnerability is one slip up in an otherwise near flawless implementation. It's a defense in depth. Design and code are a model and an inspiration, and we thank OpenSSH developers for their exemplary work. Really cool. These people are giving them a shout out for doing good work. We discovered a vulnerability. They're not bashing OpenSSH, which is awesome. They do good work. We discovered a vulnerability, a signal handler race condition in OpenSSH server, SSHD. If a client does not authenticate within the login grace time seconds, 120 by default, 600 in old OpenSSH versions, then SSD SigAlarm handler is called asynchronously. But this signal handler calls various functions that are not async signal safe. I didn't know what this meant. This was one of those things we had to look up. And if you guys don't know what it is, leave a comment if you're watching this on YouTube, or let me know here live if you're here live with me. And we'll actually do a video on this maybe on Saturday, because I also did not know what async signal safe was and meant to the Linux kernel until earlier today. For example, syslog. These race conditions affect SSD in its default configuration. It's specifically in the default configuration. We'll get into it a little bit later, but the reason is this is a timing attack, and it requires understanding the timing. So if you don't know the timing, like if you change this default from this 120 default, then actually timing, even with knowing the 120, it's like 1 in 10,000 chance, or 1 in 100,000, I think. Even with knowing the timing, it's 1 in 100,000. If you don't know the timing and you had to guess by millisecond, you just went up exponentially. It just gets so much harder. Anyways, let's continue on. On investigation, we realized that this vulnerability is in fact a regression of the 2006 CVE. Signal handler race condition in OpenSSH before it allows remote blah, 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 blah. Yeah, it's the same thing, which was reported, by Mark Dowd. I'm going to go with Dowd. Good job, Mark Dowd. Excellent work. This regression was introduced in October 2020. This is actually kind of the scary part. It's been out there for 4 years. If you've been keeping up to date, you made yourself vulnerable with the regression, which accidentally removed an this is C for you. An if-def Do log safe in SIGHand. This is terrifying. This is terrifying. From SIGDI, a function that is directly called by SSD's SIG alarm handler. In other words, OpenSSH is vulnerable to a signal handler race condition. Again, if any of these words you don't know, let me know. Like if you don't know what a signal handler is in the kernel, let me know, and we'll cover it in follow-up videos. This is why I want to read this, is because there's these types of things like, and if you didn't know it beforehand, if you don't know these things and how glibc thinks about them, then you wouldn't have even known to ask the question, right? I think, I guess, like, that's where the async signal safe. Like, I kind of had an idea what async signal safe means. Async obviously calls on a different thread probably, and it's safe to do that with a signal. Obviously, so like there's some intuitive, but I didn't know there was a term for it. I didn't know that there was a whole set of requirements for it. It's actually pretty cool that this stuff has been thought out pretty well in some of these glibc based stuff. So anyways, didn't even know to start asking the question until I read this. All right, so this vulnerability is exploited remotely on glibc-based Linux systems where syslog itself calls async signal unsafe functions. For example, malloc and free. An unauthenticated remote code execution as root because it affects SSD's privileged code. Right, SSHD runs in privileged mode, which if you can get it to execute your code, you can get your code executed as privileged, which is not sandboxed and runs with full system privileges. That's fantastic. They just said the exact same thing I followed up saying. My goodness, I should have just finished reading. We have not investigated any other libc or operating system, but OpenBSD is notably not vulnerable because its SIG alarm handler calls syslog-r, an async signal safer version of syslog that was invented by OpenBSD in 2001. There you go. That's very interesting. I actually, understanding what I do now of async signal safe things, and this is actually really interesting because they say async signal safer, like it's not safe, but it's I don't know what this means. I actually want to look at syslog-r versus the regular syslog, because I don't know. This is another thing we could look up. Let me know if you guys want to. To exploit this vulnerability remotely, to the best of our knowledge, not quite safe, but safer than the last time, which wasn't so safe. Yeah, I have no idea what they mean by async signal safer, but they do say it's not vulnerable because of it. Now, I have no idea what implications this means for Mac and Windows, right? Because, yeah, I have absolutely no idea. I kind of assume that I have no assumption. That's my assumption, is that I have no assumption. Okay. So to exploit this vulnerability remotely, to the best of our knowledge, has never been successfully exploited before. So basically, the 2006 one had never been exploited before. We drew inspiration from a visionary paper, Delivering Signals for Fun and Profit, which was published in 2001 by Michael Zalewski. Wait, is this the paper? Is this the paper? Do we need to read this at some point? I think we do. I think we do. Wait. This sounds really familiar. Have I read this? It's hard because maybe the only thing I'm thinking of is the for fun and profit. I feel like maybe that's overused. Do you know what's also really cheap? Bands. Bands are also cheap. Sorry, back to business. It actually literally costs me nothing. It's free. It's free. Nothing better than free. You know, cheap to me has cost. Banning's free. I get to take some of my time, but all right. Well, I'll have to actually start reading this to see if I've read this before. It sounds awfully familiar, but all right, let's get back into it. Nevertheless, we immediately face three major problems. From a theoretical point of view, we must find a useful code path that, if interrupted at the right time by SIG alarm, leaves SSD in an inconsistent state, and we must then exploit this inconsistent state inside of the SIG alarm handler. So this is actually the really, really cool part, is basically what they're doing is interrupting a handler based off of this inappropriate use of a non-async signal safe function that's being called inside of a signal handler. And basically their goal is they have to somehow, and this is the really cool part where we can learn a whole lot, they have to basically set up OpenSSH to execute the code that they want and then hit the right thing to interrupt it inappropriately. Where the stack in SSH, at least this is what I'm reading so far, the stack in SSH is set up in so that their code gets executed because of the inappropriate interruption. Interruptions are so inappropriate, children. Let me tell you, just don't do it. Just don't do it. All right. From a practical point of view, we must find a way to reach this useful code path in SSHD and maximize our chances of interrupting it at the right time. From a timing point of view, we must find a way to further increase our chances of interrupting this useful code path at the right time remotely. All right. Yeah. So they're saying over the network. When I read remotely here, over the network. To focus on these three problems without having to immediately fight against all modern operating system protections, in particular ASLR and NIX, we decided to exploit old OpenSSH versions first. Okay, cool. So basically they're trying on older systems. I'm guessing with the 2006 version. Yeah, with the 2.0 that had the old one first. This is the first Debian version that had a privilege separation enabled by default and is patched against all the critical environment. Okay, so this is actually a really, really cool take, and I think for two reasons. One, hopefully by the end of this, we'll understand better if modern OS protections have mitigated some of these by default. I don't know if I've not read the whole thing. So like, that's like maybe one of the bigger things is like, you know, like they were saying with FreeBSD. Obviously, FreeBSD gets a pass because they don't use the same syslog. But you know, maybe there's something else in modern Linux that would prevent this. That would be really cool. All right. To remotely exploit this version, we interrupt a call to free with SIGalarm inside SSHD's public key parsing code. Leave the heap in an inconsistent state and exploit this inconsistent state during another call to free inside of the SIGalarm handler. All right. So basically, wait. To remotely exploit this version, we interrupt a call to free with SIGalarm inside of SSHD's public key parsing code. So this is like when you're giving it a public key, okay, and it's parsing that code. Got it. Leave the heap in an inconsistent state and exploit this inconsistent state during another call to free. So they're having to trigger the other free inside the SIGalarm handler while the public key is getting parsed. Okay. In our experiment, it takes about 10,000 tries on average to win this race condition. Oh, man. With 10 connections, max startups accepted per 600 seconds login grace time, it takes 1 week on average to obtain a remote root shell. Okay, 1 second. Let's copy this. This is like a piece of information. We need to make a board of like key facts so that we can reference them. All right, key fact 1. This one here. We got it. I don't know how long this investigation went on. if even just doing this takes a week on average, like how many times did they have to try this? That's a lot. And another interesting thing here is it takes 600 seconds because you can only try, because it's at the end of that 120 grace period. 120-second grace period. This is where I was saying back here. This is where I was saying with the intrusion detection. This should be a really easy pattern to detect and shut down, right? Like it should be really easy in theory. Oh, you know what? My screen is not. That is weird. I don't know why it was off to the side like that. Sorry, I was cutting off some words. Let's cut them off. All right. Second, okay, so they did a newer one. This is the last Ubuntu version that is still vulnerable to the 2006. Okay, so this was Debian. Then they did it with different Debian. Wait. Yeah, okay. So this was Debian. This was Ubuntu Debian. All right, and then they did Deb 12 with it. Okay, we can, let's see if it takes about 10,000 tries. Okay. Oh, interesting. Why would this, if it takes about 10,000 tries here, 10 connections. Oh, this is 120 seconds. This is the 600 seconds. Okay. So this one's the default of 120, which only takes 1 to 2 days on average. All right, and then this one, it takes about the same number of tries. It's how fast you can get through those tries. So 3 or 4 hours with 100 connections. So this one just allows more connections. Ultimately, it takes 6 to 8 hours on average. Okay, that's cool. That's interesting. This it's still a work in progress. We have targeted virtual machines only, not bare metal servers, on mostly stable network links. I suppose that could make it slower. Yeah. We are convinced that various aspects of our voice... Actually, okay, with a timing attack, unstable networks could make you safer because they're having to hit that 120 seconds or whatever the default time is perfectly. And so I could actually see where an unstable network could make actually leveraging this attack harder than the stable one because you're trying to time that interrupt. Okay, cool. All right, we have convinced that various aspects of our exploits can be greatly improved. We have started to work on an AMD 64 exploit, which is much harder because of the stronger ASLR. Okay. A few days after we started to work on our AMD 64, we noticed the following bug report in Open SSH Public Bugzilla about a deadlock in SSD's SIG alarm handler. Just hate it when zombies in your program are the worst, right? It's just the worst. Gotta hate it. We therefore decide to contact, I was gonna say like they spread and multiply, but then I was like, that's really not what zombie processes do, right? They don't eat brains, they don't spread, they don't process, and they don't even moan. I feel like zombie is just actually a terrible name for them. Not to like reflect on that, but like who would that actually knows what a zombie process is think of it as a zombie, right? This just struck me. I think the zombie is a bad name for it. Moving on. We therefore decide to contact OpenSSH developers immediately to let them know that this deadlock is caused by an exploitable vulnerability. We put our ARM64 work, or AMD 64 work, on hold, and we started to write this advisory. But that is not like me. I'm breaking free. Is that like a Batman villain? The Interpreters? The SIG alarm handler of this OpenSSH version calls packet close, which calls buffer free, which calls X free, and hence free, which is not async signal safe. Oh gosh. Okay. calls packet close, which calls buffer free, which calls X free, and I love the and hence, like, of course, X free calls free. And I guess free is the thing that is not async. So I guess this is just like the code snippets from the different places. So this is what this is the okay, so this is the alarm handler. This is the packet close, which then calls buffer free. It calls buffer free a bunch. Oh, I bet this is the problem right here, right? This is what they're going to manipulate, right? Because they have a bunch of these buffer frees in a row. I only know this because of the most rudimentary things, but things in a row means that if one of these does something it shouldn't do, these still get executed probably. That's what I'm guessing. And if they're pointing to bad memory, then you get to execute bad memory. That's my guess. Buffer free in the buffer. Okay, yeah, we're just stepping through the buffer free. And this is buffer free, which calls X free, which calls free. Of course. Wait, what does X free? Why X free? So we have a void pointer. If pointer equals null, X free is just basically I was going to say safe free, but it's going to fatal. Okay, that's fine. And buffer free is okay. So this is just zeroing the buffer before freeing the pointer. Okay. This is just pretty standard C. Consequently, we started to read the malloc code of this Debian's glibc to see if any first calls to free can be interrupted by a SIG alarm and exploited during a second call to free. Inside the SIG alarm handler at lines there. That's right. If there was question mark operators, this would be solid. If this was Rust, it'd just be solid. Inside the SIG alarm handler at 341. Yeah. I'm calling it the multiple lines to buffer free because right here, your mem setting buffer points. Because this is glibc's malloc is not hardened against unlinked technique pioneered by Solar Designer in 2000, we quickly spotted an interesting code path in chunk free, which is called immediately by free. I don't know what chunk free is. An interesting code path in chunk free. Chunk free isn't in here, is it? Yeah. So this must be in one of these like memset or in free. Not sure. Okay, yeah. So this is just the forward, backwards pointers here. The size of the previous chunk, if free, size in bytes, including overhead, double linked list. That's what it looks like. We need to write some C. We need a project for C. What should we do in C? I actually want to write some C. Because it's such a good learning experience. What should we write in C at some point? Leave a comment if you're watching later, or leave something in chat right now if you're one of the cool kids that joined live. All right, define unlink. P, BK, FD. So chunk free takes an arena. Oh, so these are memory arenas. Oh, fantastic. Our brains are going to hurt after this. Like I said, I want us to take little pieces of these to remember to do other videos on, because I feel like this would be super overwhelming. And if you're feeling overwhelmed right now, I encourage you to stick around, because I too don't. I've done a lot of programming over my years. I have programmed for a while, and before that I was a chemical engineer, and before that I was a saw blade washer, and then before that I was a lost child at a college, and before that, I was just a lost child. So I don't know where I was going with that rant. I don't know why. I'm just saying that you can have a ton of experience, and it's okay to say you don't know, and some of these things are confusing. I've only been into Linux for a few years now, and some of this I think is glibc, some of this is Linux, some of this is I don't know. We'll have to learn. So if you're feeling a little lost, don't worry. I want you guys to talk about things that you specifically didn't understand so that we can maybe not cover it today, but in the future dig into some of those things and learn them and understand what they're talking about. Chemical engineer, like, can I tell you that licking our product probably won't give you cancer? That was my job specifically. Was if we got sued because a child licked our product, could we say we did our best to know everything that was in that and that those things weren't on a list that caused cancer? And then I also had to test all the parts. That was part of the due diligence, was doing some tests to make sure that they were what the supplier was giving us. It was terrible work. Absolutely terrible. Oh, worst work ever. Okay. Let's get back to this. I forget. We were looking at chunk free. We saw this, pioneered by this. We quickly spotted an interesting code path in chunk free. It is actually interesting. I like chemistry, I like physics, and I like math. And I like all those things. But one thing that I found was the implementation of the jobs that you could get without getting your PhD. And I'm not smart enough to have my PhD. The jobs you could get without your PhD were pretty boring and pretty repetitive and pretty like down to like, I put a drop of this on it, and if it didn't turn purple, then it was fine. And like, yes, there's interesting chemistry that goes into what the drop of whatever you put on it. But in the end, what you did all day was you picked 50 random parts, you put drops on them, gave them 20 minutes, and waited to see if they turned purple. That was a large portion of the job. So this is where it's like, yeah. And then like, okay, they have electroplating bath, like making sure that like the chemicals are in the right balance to electroplate well. You got some interesting work out of it, but not a whole lot. All right, let's get back to that. Let's get back to this. I thought about doing something with computer science with chemistry, but I haven't figured out anything. Like I said, I would have to do like something PhD worthy. Not smart enough for that. I can barely go under chunk free without making jokes about throwing chunks and how it's freeing. That's all I can think of with chunk free. I did not lick anything either, just so we're clear. I did not need to lick. When I said put drops on something, I was not talking about my saliva. Gross. All right. It's a sea hunk. That's right. Yeah. That Sergeant Pepper, that's what I think of chunk free. That's 100% what I think of chunk free. A free sea hunk? This stream has degraded quickly. He's a free sea hunk? He's a free sea hunk because his partner left him for rust. Oh. We got the M-Chug pointer with the AR pointer. Okay, I'm sorry. Like I said, yes, which is called internally by free. MC Hunk Direct. Okay, let's keep learning. We've digressed. What's the interesting thing that they're calling here? So check this out. We have an unlink. We have a PBKFD, a P, BK, and FD. So we have our back pointer, our forward pointer, and our pointer pointer. I'm assuming that's what that is our pointer. Like, this is our pointer, this is our back pointer, and this is our forward pointer. And yeah, back, forward. So this is our next. Okay, so this is our next, back and forward. And you can see that our back is getting set to our next is back. And then our forward is getting set to the next forward. Our forward back is getting set to back. And our back forward is getting set to forward. Okay. So that is what the unlink is doing, which would basically, it's basically orphaning off that data as you go. You're unlinking it, you're unchaining it as you go. So this makes sense. To exploit this code path, we arrange for SSHD's heap to have the following layout. Chunk X. I told you they were going to pack the stack, right? That's what they're doing. They're packing the stack to execute the code they want to have executed. The following, I'm sorry, I'm getting excited because these people are brilliant. Chunk X, Chunk Y, and Chunk Z are malloc-aided. So interesting fact here. My wife, when we named my son, I wanted to call him Maleic because I find maleic acid to be very interesting. And she said, no, that's too nerdy. And then I said, how about Malik? Because that's also pretty cool. And she said, no, that's too nerdy. So that's how we came up with Malik, which is a little bit different because it's the combination of malloc and maleic acid spelling the back end. Pretty fun. He has a super nerdy name. There you go. Naming is hard. My children have suffered for it. Chunks of memory and P, S, F, and B are their... I lost the plot here. We're going back. To exploit this code path, we arrange for SSHD's heap to have the following layout. Chunk X, Chunk Y, and Chunk Z are malloc-aided chunks of memory, and P, S, F, B are their previous size, front and forwards and backwards fields. Okay. So these are, this is Chunk X, and this is their previous size, forward and backwards. Okay. And this is the user data here. Okay, cool. Awesome. First, if a call to free chunk Y is interpreted by sig alarm after lines, but before these lines, then chunk Y is already marked as free because chunk Z's previous in-use bit is... Oh, okay. So check this out. This is also fantastic ANSI art. Because these are in a linked list, right? And so then chunk Y is already marked as free because chunk Z's previous in-use bit is cleared because of the unlinking. Okay. So this makes complete sense, right? So basically, Z is unlinking and Y is effectively getting cleared out, or is getting marked as freed. Okay. In other words, chunk Y forward and backward pointers still contain user data, attack controlled data. So they're basically using this to get their data where they want to. This is how they get the remote code execution. Oh my goodness. Now, what I'm going to ask here, and I hope they go into, how do they get it looking like this? Like they're manipulating the stack remotely. That boggles my mind. I couldn't even do it if I was holding SSHD in my hands. If I got a physical edition of SSHD, I don't think I could get its memory like this, and they got it over the network somehow. So hopefully they go into that. Or wait. They are manipulating the heap. I said stack, didn't I? They're malloc-aiding. I said, I'm sorry. Don't listen to anything that I'm saying. They're mallocating. My bad. Thanks for bringing that up. We're just talking about heap, and I don't know why I said the stack at all. My bad. We've only been talking about the heap at all. Which is why they're mallocated. I actually love this. I've never seen this. We're getting there, .rob. Hopefully we get it explained a little bit. Set data has to put some chunk of memory. I understand the concept. I'm saying it's pretty cool to like actually finally craft the data to put it exactly where you want in memory, right? Like I barely can get Rust to not complain that I haven't leaked memory somehow, and they're finally crafting data over the network. I was trying to be bombastic for making it fun. I get the theory on how they do it. All right, second, if inside the sig alarm handler, packets close calls free chunk X, then the code block at these lines, 3230. There isn't a 3230. Oh, wait, 3230. Okay, so we're skipping some lines here. Is entered because chunk wide is marked as free and chunk Y is unlinked at lines. A so-called AA4BMO primitive. What is this? This is going on our list of things to investigate. AA4BMO? All right, quick. Does anybody know this off the top of their head? If you don't respond within the next 10 seconds, I'm going to assume that you ChatGPT'd it. It says it right after it. I saw. I still don't know what it means. Almost arbitrary 4-byte mirrored overwrite. Like I get the words. I understand the words. It's okay. Almost arbitrary 4-byte mirrored overwrite. If it's almost arbitrary, doesn't that mean it's not arbitrary? So this is kind of a contradictory statement. Like that's like saying almost a lie, but then I guess it's not a lie. So I never understood that. Because chunk Y's forward and backward pointers are still attacker controlled. For more information on the unlinked technique and the okay, we're gonna slap this into our doc of things to look up later. Cool. With this A4BMO, that's what we're going to call it. A4BMO primitive, we override the glibc's free hook function pointer. Okay, so basically ASLR and NX are going to keep this from happening. Because with the address of our shellcode in the heap, thus achieving remote code execution during the next call to free in the packet close. Now we're talking over here and they got complete control. I don't know who they're talking about. To mount this attack against SSHD, we interpret a call to free inside SSHD's parsing code for a DSA public key. Okay, yeah. And exploit it during one of the free calls in packet close. Initially, however, we were never able to win this race condition, i.e. we interrupt the free call at line 144 at the right time. So basically, initially they're saying they were never able to interrupt this at the exact right time. That makes sense. Eventually, we realized that we could greatly improve our chances of winning this race. The DSA public key parsing code allows us to call free 4 times at these lines. And furthermore, SSHD allows us to attempt 6 user authentications. If any one of those 24 calls, so 6 times 4, free calls is interrupted at the right time, then they'll later achieve remote code execution inside. So basically, they're just blasting the server with more calls instead of doing it one at a time. With this improvement, we finally won the race condition after roughly one month. One month? They let this thing run for a month? That's pretty awesome. We were pretty happy. We did a root shell dance. I don't know. Is this an actual thing? Is a root shell dance an actual thing? But we also felt that there was still room for improvement. We therefore implemented the following threefold timing strategy. Okay. We do not wait until the last moment to send our rather large DSA public key packet to SSHD. Instead, we send the entire packet minus 1 byte, the last byte, long before the login grace time. And we send the, okay, so they're getting the whole big chunk sent over and then sending the last byte really quickly at the end. That makes sense. It's going to let you time it much better and much quicker. It's going to minimize the effects of network delay. Yeah. That makes sense. That makes sense. We keep track of the Nagel algorithm. Let's put that as another thing that we want to do a video on. I only know this rudimentary as far as a high level. This is what I want to do with these, though, is pull out things like this, the Nagel algorithm. We disabled the Nagel. Why would that even matter? I don't even know off the top of my head why that would matter. And that's why we should. This is why I was so excited to read this. I was like, it exposes you to a lot of things to get you starting to ask questions. That's what I was excited about. To you, the timing attack for such a small window seemed much crazier than the actual heap manipulation. Nagel may change the latency delay between packets, thus makes it harder to predict when to send the last byte. Okay, that makes sense. But we still should learn about it better. We still put it on here. Expand our horizons. Why does it change the latency delay? Like, why is it doing that? We can get into that. That's not here. Not now. We'll get into that, though. And we keep track of the difference between the moment we are expecting our connection to be closed and SSHD. So basically, when they send it, they have that 120 seconds that we were talking about for most of them. And the moment our connection is really closed by SSHD, and accordingly adjust our timing, i.e. the moment we send the last byte of our DSA packet. These time differences allow us to track clock skews and network delays, which show predictable patterns over time. We experimented with linear and spline regressions, but in the end, nothing worked better than simply reusing the most recent measurement. Possibly deep learning might yield even better results. This is left an exercise for an interested reader. Are we an interested reader? I don't know. This is a fantastic write-up. More importantly, we further increased our chances of winning this race condition by slowly adjusting our timing through involuntary feedback from SSHD. If we received this response to our DSA public key packet, then we sent it too early, SSD. So basically, they're just leveraging what they get back to adjust their timing of when to send that, when to, at that instance. Okay. If we cannot even send the last byte of our DSA packet, then we waited too long. If we sent the last byte of our DSA packet and received no response before SSHD closes our connection, then our timing was reasonably accurate. So they want to keep their times in this. Okay, that's super cool. Yeah. Dot Rob. That's all I was saying is like that's why I'm keeping this list is like let's learn about those things. But like let's not always stop to talk about them in too much detail. I mean, unless if like it's really pinnacle. I think what you said makes it is perfect. It changes the latency delay, which would cause them troubles trying to time something, right? That makes sense. Over the network. This feedback allows us to target what to call the large race window. Hitting it does not guarantee that we win the race condition, but inside this larger window are the 24 small. Because I'm sorry, now my brain just going. What I thought Nagel did made it more consistent. I didn't think it made it less consistent. This is, I guess, why I don't understand. Because I obviously don't understand what the Nagel algorithm was doing in the first place. So I think I completely misunderstand it. So I need to do some research. All right, this feedback allows us to target what we call the large race window. Hitting it does not guarantee that we will win the race condition, but inside this large window are the 24 small race windows inside the 24 free calls that, if hit, guarantee that we win the race condition. That it works every time when you actually do it. With these improvements, it takes 10,000 tries on average to win this race condition. Yeah, it takes 1 week on average to remember. And you know what? Like, this sounds like a really long time. But in actuality, if I said that I could hack in reliably, and I'm going to say within a month to any company using SSHD, like, that's actually a pretty big deal. I don't care that it took me a month. And, this is something that you set and forget, right? You just spin it up in AWS or GCP or wherever and move on. Like, this is terrifying. And the reason I said a month is something people don't think about. When they say it takes roughly a week or on average a week, that means it could take a month. That means it could take the very first try. With these types of things, it could take you 2 years. Like, that's a possibility. It's not likely, but it could, right? So keep that in mind. Like, it could take longer or it could be instantly. All right. So this is moving to the Ubuntu version. Theory, take 1. The sigterm handler of this OpenSSH version does not call packet close anymore. However, this Ubuntu's glibc always takes a mandatory lock when entering the functions of the malloc family. Always takes a mandatory lock when entering the function of the malloc family, even if a single-threaded like SSHD, which prevents us from interrupting a call on one of the malloc functions and later exploiting it during another call to these functions. We must find another solution. So this is really cool. We're stepping through the history of glibc, the different things put in place, and the different ways that they're getting around those things. Amazing. 2006 mentions a double free in GSS API, but GSS API, or Kerberos, is not enabled by default, so this does not sound very appealing. On the other hand, PAM is enabled by default, and PAM end is called by SSHD sigterm handler and is, of course, not this comes up again, async signal safe. I wonder if there's a async signal safer version. We therefore search for a PAM function that, if interrupted by sigterm at the right time, would leave. This is amazingly diligent work. Would leave PAM's internal structures in an inconsistent state. Exploitable during PAM end. In the sigterm handler, we found PAM set data. PAM set data takes a handle to PAM. The panhandle for you Floridians out there. A void cleanup. Okay, so some function to a cleanup. Okay. Clean it up. If this function is interrupted by sig alarm after line 66 and before line 77, then data entry is already linked into PAM's structure, PAMH. But this cleanup field, a function pointer, is not yet initialized since the malloc at line 57 does not initialize its memory. We are able to control cleanup through the leftovers of previous heap allocations. Then we can execute arbitrary code with PAM-end. Inside the signal term, sig alarm handler calls a PAM-free data at line 118. Okay. So while data, clean it up. Let's clean it up. That's how we free PAMs. That's it. We've been an extremely simple exploit. Unfortunately, we completely overlook that PAM set data can only be called from PAM modules. If we interpret it with sig alarm, interrupt it with sig alarm, then the PAM handler is still PAM called from module. In which case, PAM-end returns immediately without ever calling PAM-free data. Back to the... I hate this when this happens. Like, you're on such a roll. You're like, oh, this is so totally possible. And I'm so glad they put this in here. I'm so glad they put this in here because this is just like a breath of fresh air for me because this happens to me where I'm like, oh, this is... And like, there's just one little thing where it's like, no. Take two. Not giving up. It's not what we do. This is like some movie. They're quoting it. Album. I guess they sing. Okay. Band. It's a band. This guy loves them a lot. We notice that at line 601 below, SSHD passes a pointer to its global SSH PAM handler pointer directly to PAM start, which is called once per connection. There's your PAM start per connection. We therefore decide to look into PAM start itself. If interrupted by sig alarm, we might leave the structure pointer to... If interrupted by sig alarm, it might leave the structure pointed to by sig PAM handle in an inconsistent state, which could then be exploited inside of the sig alarm handler. When PAM end, the SSH PAM handle, SSH PAM error is called. I'm not going to read through all this code. I'm going to take their word for it. Oh, I mispronounced their name. They're the interrupters. That makes sense. It's not even that they like them. I read it as the interpreters because I'm an idiot. 100% read this as the interpreters the entire time. But it's the interrupters. This makes sense now. This makes sense. It all makes sense. All right. I'm sorry. I didn't get it. And it's brilliant. It's brilliant. They put in so much work to get the right quotes for each of these sections. This person is a storyteller. Or the interrupters have like a lot of music that made it easy. I don't know which one it is, but okay. Back to take two. All right. Well, I'm an idiot that can't read. We know this. We'll move on. Not the interpreters. Interrupters. All right. We therefore decide to look into PAM start itself. If interrupted by sig alarm, we might leave the structure pointed by... Oh, wait. We already read that. We were right here. Right. At line 32, PAM start immediately sets SSHD's SSH PAM handle. PAM handle. To a calloc. If you guys don't know, Florida, the long skinny part, at the top is called like the panhandle. That was the joke that I was going for, but that would only make sense to Americans. So I'm sorry if you're not from America and didn't get the joke. All right. To a calloc mallocated chunk of memory. This is safe because calloc initializes memory to 0. On the other hand, if PAM add handler, which is called multiple times by PAM start, is interrupted by sig alarm after line 800, this is dedication, like understanding. I hope this person mind mapped this out, because I have mind mapped out the execution flow. I know I notoriously show off the one I did for the consensus bug, where we kind of had that 3-dimensional graph of the flow to understand how we got the bug. I hope they did that, because this is seriously mad levels of understanding the flow and order of operations. This puts the order of operations in math to shame. To shame. Okay. Is interrupted by sig alarm after line, but before line 886, then a mallocated structure is linked into PAM-H, but its next field is not yet initialized. If we are able to control next through leftovers from previous heap allocations, then we can pass an arbitrary pointer to free during the call to PAM end. This amount of coordination, one thing that's really impressive here is, remember, they're manipulating this through the network. So something that's kind of delayed, a little bit networky stuff. And we're talking about lines of code, between 874 and 886. This could happen in a blink of an eye. I don't know what happens. I don't know. Maybe there's a heavy lifting thing here that actually takes a millisecond. But most lines of code happen instantly. Like, instantly. So anyways, that's just impressive. That's just impressive. Because the malloc of the Ubuntu glibc are already hardened against the old unlink technique, we decided to transform our arbitrary free into the malloc's mallification house of mind fastbin version. We free our own non-main arena chunk, point our fake arena to SSHD, got an overwrite exits entry with the address of our shellcode in the heap. This Ubuntu's heap is still executable by default. For more information on mallification, we're going to put this. I think every single link this person puts in here, we're going to have to read in the future and understand better. The interrupters. Who would have guessed? To mount this attack against SSHD, we initially faced 3 problems. The house of mind requires us to store the pointer of our fake arena at address here in the heap, but we're not able to store attacker-controlled data in such a high address because SSHD calls PAM start at the very beginning of our user authentication. We do not control anything except the username itself. Luckily, a username of length 128 kilobytes allows us to store our own data at... I love these types of things where it's like, what if we just put a bunch of data in there? The size of our field, our fake non-main arena chunk must not be too large to pass freeze security check. It must contain null bytes, but our long username is a null terminated string that cannot contain null bytes. Luckily, remember that PAM-free handler's auxiliary zeros the structures that it frees. We therefore patch the size field of our fake chunk with such a memset 0 and only then free it. I'm posting this in here. We're not going to sit here until I need to think on this. The size field of our fake non-main arena chunk must not be too large to pass freeze security checks. It must contain null bytes. But our long username is a null terminated string that cannot contain null bytes. Look, wait. But our long username is a null terminated string that cannot contain null bytes. Right. This is the problem. So they have to get they have to remove the null bytes. Luckily, remember that PAM free handler's auxiliary zeroes the structure that it frees. 1019. We therefore patch the size field of our fake chunk with a memset 0 and then only free it. How do they do this? How do they do this, right? They're on the network, right? How do they memset 0 and then free their... I don't get this part. Let's read on and see if they say. We must survive several calls to free at lines 1017, 1020 above before the free of our fake non-main arena chunk. We transform these frees into no-ops by pointing them to fake ismap chunks. Free call. So this is all data stacking with... My guess here is that this is all data stacking with the username memory, right, in the heap. So they're very specifically giving exactly what data they want through this chunk of memory. It is my understanding at this point, which calls mum map, which fails because I don't know what this is. This is fake is immapped. Chunks are misaligned, effectively a no-op because assertion failures are not enforced in this glibc. Oh. Sure, assertion should be fat. Okay, finally, our long username also allows us to control the potentially uninitialized next field of 20 different structures, the leftovers from temporary copies of our long username, because PAM start calls PAM add handler multiple times. Our large race windows contains 20 small race windows. So basically, they were able to use this to hijack 20 different structures to give them 20 windows instead of just one. That's actually pretty ingenious. Same tricks they used before. The interrupters. From this attack against Ubuntu 6, we simply reuse the timing strategy we used against Debian. It takes 10. And this is why it took only 1 or 2 days, because we were talking about how that was weird, and that it was so much faster because they got those 20 extra structures, which now makes sense. I really need to write more C, don't I? I do. This has the 120-second grace time. Let me do this. Made it easy to get back here. They summarized it up here. Right. This one had the 600. Wait. The first one had the 600, yeah? Yeah, 600. Oh, okay. So it was just the login grace time. It had nothing to do with that. All right, good call. I think you're right. I thought that they were saying that they got 20 different structures. Oh, they actually had 24 on the other one, didn't they? Didn't they have like a couple different race windows? That's true. That's true. So that shouldn't have done anything. Good point. Good call out. Now you're ready. Take the demons head on. Oh boy. The SIG term handler in this open SSH version. So far we've only been attacking really old stuff, right? This is like really old stuff. We haven't even gotten to modern stuff. The SIG term handler in this open SSH version does not call packet close, nor PAM end. In fact, it calls only one interesting function, syslog. All right, my throat is getting a little parched. We're about 5 minutes from it. I'm going to run an ad while I get a cup of water. I'll be right back. Because, yeah, my throat is, I've been talking a lot. I'll be right back. Welcome back from the ad. Oh, wait. Now, welcome back from the ad. All right, thanks. Okay, so wanted to talk. Well, first, I wanted to say, .rom, thanks so much for some of your insight in this. absolutely fantastic. These are things we want to learn more about, and I've appreciated some of the insight that you've been giving. So thank you. If I haven't said it before now. Second, they did state that this was at the very beginning. Let me mark my spot. At the very beginning, they stated that after a few days, we started our work on okay, so I just found it for you right here. This research is still a work in progress. We have targeted virtual machines only, not bare metal servers, on a mostly stable network. We have, which makes sense. We are convinced that various aspects of our exploits can be greatly improved. We have started to work on an AMD exploit, which is much harder because of the stronger ASLR. So they have started work on an AMD 64 exploit. None of these are. So all of these are the older 32-bit i68.6s. So they said after a few days, we started work on AMD 64. We noticed the following bug report in OpenSSH Bugzilla about a deadlock in SSHD's SIG alarm handler. We therefore decided to contact OpenSSH developers immediately to let them know that this deadlock is caused by an exploitable vulnerability. We put our AMD 64 work on hold and we started to write this advisory. No, as far as I know, they don't have the AMD 64 work. And to be honest, I'm going to be watching for it. But like, if these take a month to do, it will be 6 months before we have an AMD, right? Like, if they even continue on, right? Because like part of me is like, well, if it's already patched, it will depend on how big of a nerd they are, right? Like how badly they want to know if they can beat AMD 64, right? That's probably what it's going to be. Now, it did get an 8.6. So I think that it got an 8.6 for two reasons. One, maybe it's harder to exploit on AMD 64. Don't know. I mean, I'm assuming it is, but, you know, maybe they find a way to make it not so much harder. The other thing that, the other reason I think that I got an 8.6 is it seems very difficult. If you were doing this over the public internet to try to time it right, it sounds like it would be very difficult to actually time correctly. It sounds like they were in a very, you know, it doesn't sound like they were going over the public internet. And had a very stable network connection. So I think that's why I got an 8.6 instead of a 10 out of 10. Those are my guesses. But an 8.6 is still a high enough vulnerability that you should assume that an AMD 64 can be done. At least that's my assumption. All right, so we got syslog. And not syslog R, because syslog R is safer, whatever that means. Our two key questions then. Does the syslog of this Debian's glibc call async signal unsafe functions such as malloc and free? And if yes, does this glibc still take a mandatory lock when entering the functions of the malloc family? Luckily for us attackers, the answer, luckily for us attackers and unluckily for the rest of you is what they're saying. The answer to our first question is yes. If and only if the syslog inside the sigterm handler, sig alarm, I don't know why I keep saying sigterm, I'm so sorry. SIG alarm, it's been a very long day, and I wanted to do this. So even though it's been a long day, I was like, people should get this immediately. Handler is the very first call to syslog. Then local time 64R, which is called by syslog, calls malloc to allocate a file structure at line 166 and calls malloc to allocate an internal read buffer. All right. No, because we do not control anything about these mallocations, not their order, not their size, not their contents, we took the RCE at line 166 as a much needed good omen. Wait. And lucky for us, the answer to our second question is no. Since October 2017, the glibc malloc functions do not take any lock anymore when single-threaded, like SSHD. This is interesting. This is really interesting implementation detail of malloc. Yeah. Moreover, this probably sped it up quite a bit, right? And I'd be interested into what CPU feature or whatnot that they're leveraging to ensure that it's safe in theory. Moreover, this Debian version suffers from the ASLR weakness described in the following great blog post by Justin Miller and Matthias Rouse, respectively. We're gonna put these for future readings. We have this one blog post, not blog post, but this one thing has given us so much future learning. I'm super happy that they did such a good write-up with so much, like they have for us unintelligent ones put out so much of the different links and stuff for us to learn from. I'm super happy about it. In this case of SSHD on an i38.6, every memory mapping is randomly normalized. SSHD's pi, the heap, most libraries, the stack. But the glibc itself is always mapped either at address here or at address here. In other words, we can correctly guess the glibc address half of the time. A small price to pay for defeating ASLR. In our exploit, we assume that the glibc is mapped to address here because it is slightly more common than here. That's interesting. This statement I find interesting, right? This I find interesting, right? Why? And I know this is just like probably inconsequential. But why can they state this? In our exploit, we assume that glibc is mapped here because it is slightly more common than here. Why is this more common than this? Why is 7.2 million more common than 74 million? And I know it's byte. I get it. It's not that actual number, but I don't know. Now I'm really interested. And they just state it as fact. In our next question, which code path inside glibc malloc function, if interpreted by sig alarm at the right time, leave the heap in an inconsistent state, exploitable during one of the malloc calls inside of sig alarm handler? We found several interesting and surprising code paths, but the one we chose involves only relative sizes, not absolute addresses, unlike various code paths inside unlinked chunk, for example. Rob, probably depends on how and where the dynamic linker puts the libs in memory. I get that. I just don't understand why it would favor one. Like, it seems to favor one like 60-40. Again, they don't give an exact number, but it seems like an odd thing to say it favors one, right? Because it must be deterministic that it favors one. But then what type of algorithm is deterministically favoring one for random allocation? Like, that's I guess what my brain goes down. Why? Obviously, these researchers understand it well, and that's cool. This code path inside of malloc splits a large free chunk into two smaller chunks. The first chunk is returned to malloc's caller at line there, and the second chunk, or remainder, is linked into the unsorted list of free chunks at these lines right there. Wait. 4324. Okay. So this is the backwards and forwards pointers. Again, this is going back to that chunking that we're talking about here. Okay, this makes sense. We've seen this code not this code specifically, but we've seen the chunking code. We've all blown some chunks. That's all I'm gonna say. It's happened. It happened here. If this code I'm sorry. That was a joke. If this code path is interrupted by a sig alarm after line 4327. So after we set the remainder to the back pointer here, but before 39, where we're setting the head. Okay. So what? 12 lines of code? And if all of these are like just pointer math, they're really fast lines of code. Really fast lines of code. Then the remainder chunk of this split is already linked into an unsorted list of free chunks. But its size field, memchunk size, is not yet initialized. If we're able to control its size field through leftovers from previous heap allocations, then we can make this remainder chunk. We need to do a heap allocation thing. We so need to do this at some point. We can then make this remainder chunk larger and overlap with other heap chunks, and therefore corrupt heap memory when this enlarged. I read that poorly. And therefore corrupt heap memory when this enlarged. Overlapping remainder chunk is eventually mallocted and written to... I'm not reading that well. I mean, it makes sense. It was rough for me to read. Our last question then is, given that we do not control anything about malloc calls inside of sigterm handler, what can we overwrite in the heap to achieve arbitrary code execution before SSHD calls exit? Validates a file structure in the heap, 166 above, and because file structures have a long history of abuse for arbitrary code execution, we decided to aim our heap corruption at this file structure. This is, however, easier said than done. Our heap corruption is very limited, and file structures have been significantly hardened over the years. Eventually, we devised the following technique, which seems to be specific to the i38.6 glibc. The AMD 64 glibc does not seem to use vtable offset at all. So this current one only is the i386. Interesting. With a limited heap corruption, we overwrite the vtable offset field, file structure, the glibc, libio functions, libio functions will therefore look for this file structure's vtable pointer, a pointer to an array of function pointers, at a non-zero offset, our overwritten vtable offset, instead of the default 0 offset. Makes sense. We attackers can easily control this fake vtable pointer through leftovers from previous heap allocations because the file structure around this offset is not explicitly initialized by fopen. I love fopen. It just sounds like somebody that's really, really frustrated. Like, you know, when you've tried to open something for a little while, you just got to use fopen. Like, that's why it always makes me smile. I'm such a juvenile sometimes when I'm looking at these things. I'm sorry. Moving on. Making it child-friendly again. To pass the glibc's security checks, our fake vtable pointer must point somewhere to the libio vtables section. We decided to point it to the vtable for a wide character stream. Since we assume that glibc mapped out address this. Okay. So they're going here since they're making this all on the assumption that they're here. So basically, if glibc mapped to the 72 address, then this attack just wouldn't work. Penguin, thank you so much for the follow. Thanks for joining us on this incursion of learning. This is a little dry. I get it. I'm super excited because we actually have a bunch of things that we have to learn about, and we'll do future videos on. I think we've pretty much covered the meat of this thing, but the bigger thing here is this has given us things to just investigate, research, and understand moving forward. So anyways, yeah. In summary, by overwriting a single byte in the vtable offset of the file structure allocated by fopen, we can call our own FCT function pointer and execute arbitrary code during read unlocked. I wanted it perfect. No wrinkles in it. The interrupters. To mount this attack against SSHD's privileged child, let us first imagine the following heap layout. Oh boy. Oh boy. The X's are barriers, chunks that allow us to make holes in the heap. For example, small memory leak chunks. XXX, large hole, roughly 8 kilobytes. XXX, small hole, another triple X. Shortly before SSHD receives a SIG alarm, we mallocated a 4 kilobyte chunk that splits the large 8 KB hole into small. Wait. Shortly before. Okay, so they're splitting this. They're splitting this larger hole into a smaller chunk, a 4 kilobyte chunk. So they're just splitting this in half. They state these things so simply. How did they get it to mallocate this in the middle? Like, how did they? I know that they did it over the network, but how did they do that? How did they manipulate it over the network to get another? Because basically what they had to do is find some way to trigger another malloc here, right? So we still have a 320 byte small hole. But if this malloc is interrupted by a SIG alarm after this line, but before this line, then the remainder chunk of this split is already linked into the unsorted list of free chunks, but its size field is under our control. Through leftovers from previous heap allocations, this artificially enlarged remainder chunk overlaps with the following, the small hole, this 320 bytes. So basically, when they do this malloc and they interrupt it, they get to write. They get the ability to write how large the chunk is, which then they expand it here. Artificially large remainder chunk. When the SIG alarm handler calls syslog and hence tz file read, fopen mallocates the small hole for its file structure, and freed unlocks mallocates a 4 kilobyte read buffer. Okay, so this is the sequence they use to get those 4 kilobyte read buffers, thereby splitting the enlarged remainder chunk in two. And that's when they have to hit the right timing to interrupt it right there. That's amazing. I think they just send a big response, which SSHD puts in. Yes. I think you're actually absolutely right, Rob. I was just getting there. I wasn't getting there, and I finally did. We therefore overwrite parts of the file structure with the internal header of this small remainder chunk. More precisely, we overwrite the file's vtable offset with the third byte of the header's bk field, which is a pointer to the unsorted list of free chunks. Then, as explained in the theory subsection, freed unlock calls IOW file underflow instead of IO file underflow, which calls our own FCT function pointer and executes our arbitrary code. More pressing problem. Indeed, we learned through our work that older open SSH versions that we will never win this signal handle race condition if our large race window contains only one small race window. So basically they're saying here is if there's only a single point, we were talking that there's only 8 lines of code. It's like from here to here, from here to the 39. So there's 12 lines of code that they have to interrupt between, right? From this 4327 to 4339. So 12 lines of code that is very quick execution code. You have to interrupt in between. And they're basically saying that while in theory it's possible, it probably would never happen. Yeah, but what about the quantum encryption and communication 0 days? I mean, that's a problem. It's a problem. Well, and this is why, to be honest, why I'm going over this. I think that too often us as developers have pushed off this type of knowledge and thinking because it's hard, it's complicated, and a lot of times we're just generally wanting to get our thing done, making our application. And one of the things as I've grown older is I wish that I paid more attention to this type of stuff myself. Now, like I said, I never started out as a software engineer. I learned through trial and error, and this is one of the things that I'm starting to learn more about and putting more effort into, because I think that it's important. Whether it's quantum or not quantum, it doesn't really matter. Quantum will present its own set of issues with how we do encryption, and there's already encryption, quantum safe-ish, safer algorithms out there that you can start leveraging, right? So this is something we can all learn from and try to understand a little bit better. Get better at what we do. Computer science is really actually a science. Well, I'm trying to get better. That's the goal, is to get better. So basically what they're saying here is that, well, in theory it could happen. In practicality, it won't. If our large race window contains only one small race window, it's just probably not going to happen. Consequently, we implemented the following strategy based on the following heap layout. So it looks like they're just doing it multiple times. The last packet that we send to SSHD shortly before the delivery of SIG alarm forces SSHD to perform the following sequence of mallocs. They just do it multiple times, right? If this split is interrupted by a SIG alarm at the right time, then fopen in. So basically, they just do the malloc multiple times. They set it up to happen multiple times so that they can basically try to time it multiple times, right? There's one here, there's one here, maybe there's one here. If not, then we mallocate the small hole one ourselves with the first malloc, and our second malloc splits the large hole 2 into 2. If the second split is interrupted by this at the right time, then we fopen inside the SIG alarm handler, and mallocates the small hole 2 for the file structure, and we retrieve arbitrary code explanation as above. We were able to make 27 pairs of such large and small holes in SSHD's heap. Okay, so cool. They made basically 27 of these, because max packet size, 256 kilobytes. So basically they had to keep the payload in under that size. Our large race window now contains 27 small race windows. Achieving this complex heap layout is extremely painful and time consuming, but the two highlights are: we abuse SSHD's public key parsing code to perform arbitrary sequences of malloc and free calls between those lines. We were unable to find a memory leak for our small barrier chunks. Instead, we used Tcache chunks, which are never really freed because their in-use bit was never cleared, as makeshift barrier chunks. To reliably achieve this heap layout, we send 5 different public key packets to SSHDs. A to B can be sent long before SIG alarm. Most of packet E can also be sent long before SIG term, but its very last byte must be sent at the very last moment. Right. They talked about this where basically, because timing is everything, you want the smallest thing so it gets there as quickly as possible. So these are the packets: A, B, C, D. Okay, so this is the layout of all of the stuff. We mallocate and free a variety of Tcache chunks to ensure that the heap allocation that we do not control end up in these Tcache chunks and do not interfere with our careful heap layout. We mallocated and free chunks of various sizes to make our 27 pairs of large and small holes and the corresponding barrier chunks. The C packet, we mallocated and free 4 kilobyte chunks and 320 byte chunks to write the fake header, write the fake footer, write the fake vtable. D, we mallocated and free 1 very large string, nearly 256 kilobyte, to ensure that our large and small holes are removed from the unsorted list of free chunks and placed into their respective malloc bins. We force SSHD to perform our final sequence of malloc calls to open our 27 small race windows. Alternative readers may have noticed that we'll still not addressed, and literally and figuratively, the problem of code CVT. In fact, code CVT is a pointer to a structure that contains a pointer to a structure that contains the FCT function pointer that allows us to execute arbitrary code. To reliably control FCT through code CVT, we simply point code CVT to one of the glibc's malloc bins, which conveniently contains a pointer to one of our my brain is done. My brain is done. It's done. I didn't learn anything from that. To reliably control FCT through code CVT, we simply point code CVT to one of the glibc's malloc bins, which conveniently contains a pointer to one of our free chunks in the heap, which contains our own FCT function pointer to arbitrary glibc code. All of these glibc addresses are known to us because, okay. Again, this all goes back to knowing where it was mapped at. We're running out of time. Yes, we are. Yes, we are. As we implemented this third exploit, it became clear that we could not simply reuse the timing strategy that we had used against the other older OpenSSH versions. We were never winning this new race condition. Oh. It takes a long time, 10 milliseconds, for SSHD to parse our fifth and last public key packet. In other words, our large race window is too large. Our 27 small race windows were like needles in a haystack, so they were never hitting the right time. The user-specific delay that was introduced recently delays SSHD's response to our last public key packet by up to 9 milliseconds, and therefore destroys our feedback-based timing strategy. As a result, we developed a completely different timing strategy. From time to time, we send our last public key packet with a little mistake that produces an error response right before the call to SSH key from blob that parses our public key. From time to time, we send our last public key packet with another little mistake that produces an error response. Right after that, that passes our public key. The difference between these two response times is the time it takes for SSHD to parse our last public key. And this allows us to precisely time the transmit. So they make two mistakes to then time their, this allows us to precisely time the transmission of our last packets. So the first time they were actually just doing the request and judging it from the response, and they no longer could do that. So then they had to do something else to time it. All right, cool. I think it's funny. With this change in strategy, it takes 10,000 tries on average to win the race condition. With 100 connections, accepted 120 per second, it takes 3 to 4 hours on average to win the race condition. You know what's really interesting here? Is that the harder and more secure, the deeper they had to dig, the faster they were able to make this, right? Because they kept losing different ways to do it, right? They lost the easy ways to do it, and they had to find more difficult ways to do it. But in the end, they got faster times. That's really interesting. Towards an AMD 64. So far, AMD 64 is out of the picture. We decided to target Rocky Linux 9. For two reasons. Its OpenSSH version is vulnerable to the signal handler race condition, and so in theory, it's vulnerable. I mean, it is vulnerable. It has the issue. And its glibc is always mapped at a multiple of 2 megabytes because of the ASLR weakness discussed in the previous theory subsection, which makes partial pointer overwrites much more powerful. The syslog function, which is async signal unsafe, but is called by SSHD's SIGAlarm handler of this glibc version, internally calls open memstream, which mallocates a file structure in the heap. These file structures in the heap are killing us. Stop doing it. .rom, that's really cool. If you could drop a link to that in Discord or here, that's really cool. But no, just like why it favors, even though it's still random. Like like I said, it's just that piqued my, when you say random and then it favors, I'm like, well, why does it favor? I don't know. With a heap corruption as a primitive, 2 file structures mallocated in the heap and 21 fixed bytes in glibc addresses, we believe that this signal handler race condition is exploitable on AMD 64. Probably not in 6 to 8 hours, but hopefully in less than a week. Only time will tell. Side note, we discussed that Ubuntu 2024 does not re-randomize the ASLR of its SSHD children. It is randomized only once at boot time. We track this down to a patch below, which turns off SSHD's Rex, I don't know this flag. This is generally a bad idea, but in the particular case of this signal handler rest condition, it prevents SSHD from being exploitable. The syslog inside the SIG alarm handler does not call any of the malloc functions because it is never the very first call to syslog. Very cool. And then the patching. And that's patched. Oh, cool. I'll have to do that sometime. Not today. Not today. I didn't get to any of the other stuff. That was really long. Holy crap.